Right, so this is a lesson on 4.8 conservation of momentum. All right. So this do not say is what did we learn about inertia. It's important that you remember remember what we learned about inertia in lesson 4.3. Now, if you forgot, well, here it is, right? Inertia is the tendency of an object to resist any type of change to its current motion, right? And so it's proportional to your mass, right? And so obviously, if you take a look at the top right hand GIF, right, if you have a lot of mass, you don't really want to stop, right? You want to keep going. It's very hard for you to stop this object from going. And if you look at the bottom, the baby's at rest, and the baby wants to keep being at rest, right? So that's essentially what's happening here. And velocity has no effect on inertia. Now, when I'm talking about something called momentum, now momentum is something that describes an object with both mass and velocity. So, in contrast to inertia, where inertia only was proportional to mass, momentum is proportional to both mass and velocity, right? So, the formula for momentum is P is equal to mv, where m is your mass and v is your velocity, all right? So P is your momentum, is measured in kilograms times meters per second, right? So the more mass you have, and if your velocity is constant, the more mass you have, the more momentum you have, right? And if your mass is constant, well, the more velocity, well, that means you have more momentum. And let's do these two practice questions now. Snip and sketch. Let's move this over here. So what is the momentum? Right. So what is the momentum of a 4.10 kilograms? So they're looking for momentum. Right. They're looking for momentum, and you have a mass, right? Because it says your mass is 4.5 times 10 to the 3 kilograms, right? So 4.5 times 10 to the 3 kilograms. Let's actually make this a little bit larger, maybe 7. And so it's traveling at a velocity of 50 meters per second east. And it also says, well, your time is 80 seconds, right? So you do this in 80 seconds. Well, you do this for 80 seconds. And so what is the answer here? Well, you're going to do momentum is equal to mass times velocity. Well, your mass is 4.5 times 10 to the 3 times your velocity, which is 50, right? So you're going to multiply these two. And so then you are going to get 50 times 4.5. It's going to give you something. So 5 times 4.5, 22.5. 22.5 times 10 to the 5 kg. No, it's not it. What is this actually? Let me calculate myself. Do this. 4.5 times 50. No, I am right. Okay. I don't know why I doubted myself. So it is this, right? It is this. This is the answer. Seems pretty simple enough. Nothing too hard. Nothing too hard. Alright, so what is the velocity of a 5 times 10 to the 3 kilogram car? Right, so you have a velocity of your car is 5.0 times 10 to 3 kilograms. Right, and so your momentum, right? So the car has a momentum of this, right? So your momentum is 8.0 times 10 to the 4 kilograms. Right? 8 times 10 to the 4. I'm sorry. And they're looking for was your velocity. They're looking for the velocity. I'm sorry. Even your teacher could make mistakes, I guess. That's not your velocity. So your mass, right? They're asking you what your velocity action is, right? Looking for, they're asking you to solve for your velocity. You use this formula, right? Your momentum is mass times velocity. Your momentum is 8 times 10 to the 4 kilograms. Is equal to mass, which is that, right? And your velocity is what you're trying to solve for, right? And then you want to divide by that, divide by that. You're going to get 1.6 times 10 to the 1 meters per second. Or if you do this yourself, you're going to get 60 meters per second. It is your velocity, okay? Let's move on. So the question here says, the number on top of the steel ball and the wooden block displays the momentum of the objects, right? So what do you notice about the total momentum of both objects before collision and after collision? And this is something you should have realized, right? You should have realized. Let me just get rid of this. So something you should have realized is that your momentum before collision, right? Let's take a look at your momentum before collision, right? So if you look at the bottom number, the steel ball has a momentum of 23.76, right? And the wooden block has a momentum of 0. And if you look at your total momentum after, well, the steel ball now has a momentum of 0.2, and well, your wooden block now has a momentum of 23.56. And something you should have realized is that, well, the total momentum before an object collides, before these two objects collide, is equal to the total momentum after these two objects collide, right? So the total momentum here, and the key word here is that your total momentum is conserved. Right? Your total momentum is conserved here. So your momentum of two objects before a collision, right, before they collide, is equal to your total momentum of your two objects after they collide. And here we get to the topic, right? The topic of this unit, which is the conservation of momentum, right? So the total momentum of two objects before a collision is equal to the total momentum of both objects after collision. And so you have this formula here, right? On the bottom, you have your total momentum after, right? And so let me just screenshot this, I guess. Right. Oh wait, that's not what I want. Actually, no, it is not what I want. Yeah, I want this. It's fine. So here's the thing, right? So your total momentum of both objects before a collision is equal to the total momentum of both objects after a collision. And so your momentum of the first object, the initial momentum of your first object, plus the initial momentum of your second object is equal to the final momentum of your first object plus your final momentum of your second object. Right? And only this is the conservation momentum. And so from what we learned before, where momentum is mass times velocity, then we have mass 1, initial velocity of object 1, plus mass 2, initial velocity of object 2, is equal to mass 1, final velocity of object 1, plus mass 2, final velocity of object 2. And this is our formula right here. This is what we get. This is what we get. And that is the formula. Your reference table will only have this. Right? Your reference table will only have this. It will have nothing else. And so there's a derivation, right? So conservation of momentum, all the formulas we have, they come from somewhere. And luckily enough, well, our conservation momentum can be derived actually using algebra from Newton's third law. If you want to figure out how does Newton's third law give us conservation of momentum, well, here it is. Right here it is. So you can peruse it at your own pace rather, and yeah. But we're not gonna do that. This is also unnecessary. We're not gonna. This is not gonna be on your test. It's just telling you what are the different types of collisions, right? Completely inelastic, top right, where they're stuck together. Partially inelastic, where they do crush and deform, but they do uh, they do separate, and elastic, where they don't deform and they definitely separate. Gonna move on to practice questions like we always do. Like we always do. Alright. So as represented in the diagram below, a block A with a mass of 0.100 kg. I want to call that mass 1. I want to call this mass 1. I want to call it 0.100 kg. It slides to right at 4 meters per second. Right, so the initial velocity, right, your initial velocity of this object is 4.0 meters per second. It hits a stationary block B with a mass of this. So the mass of object 2 has a mass of 1.50 kg. And after the collision, block B slides to the right and block A rebounds to the left. And at 1 meters, rebounds to the left at 1.5 meters per second. Right? Block A rebounds to the left at 1.5 meters per second. So the final velocity of object 1 is negative, right? Because it's going to the left now, right? It's going the opposite direction. And then they say calculate the speed of block B after the collision. So speed of block B. They want you to find out what the final velocity of object 2 is. Now we're missing a velocity, right? We're missing the final velocity of object 1. I'm sorry. We're missing the initial velocity of object 2. But the initial velocity of object 2, block B, right? It's a stationary block B, which means that block B starts with an initial velocity of 0. Right? It starts with an initial velocity of 0. Okay. So now we're doing our formula, right? So the momentum before an object is equal to the total momentum after the objects collide. And so P before, so mass 1, initial velocity of object 1. So actually before that, right? And if you were someone curious, well, how do I get initial? How do I get final? Well, if the problem mentions after the collision, right? And there's a very key word here, after the collision. If they say after the collision, well, then that's your momentum after, and so you can treat it as your final velocity, right? So before the collision, that's your initial velocities. And if it says after collision, well, that's your final velocity. Let's go back to the formula. So your total momentum before an object, before these two objects collide, is equal to your total momentum after these two objects collide. So the initial momentum of object 1 plus the initial momentum of object 2 is equal to the final momentum of object 1 and the final momentum of object 2. So you have mass 1, initial velocity of object 1, plus mass 2, and initial velocity of object 2, plus mass 1, and final velocity of object 1, plus mass 2, final velocity of object 2. And here we just substitute. You can see here I'm running out of space, right? This is not intended. I'm running out of space. Okay. That's plus there. So 0.1 times 4 0.4. 0.15 times 0, that's 0. 0.1 times negative 1.5. Obviously negative 0.15. Plus 0.15 VF, final velocity of object 2. So I get this. Probably decrease the make this 5, right? So plus 0.15 plus 0.15 55. What's net? Oh yeah, it's plus, so it's fine. Let me divide this, and we get 3.67 meters per second, and that is the final velocity of object 2. Okay, let's do another practice problem. Oh no. Okay, well. Wish I could zoom. Wish I could zoom out. I mean, zoom in. Or rather, zoom out. I don't know. I wish I could zoom out. I mean, zoom in. I mean, zoom out. I don't know what I'm saying. Anyway, on a snow-covered road, a car with a mass. I don't know what the parentheses there. So you have a car, and the mass of that car is 1.1 times 10 to the third kilograms. Collides head-on with a van having a mass of 2.5 times 10 to the third kilograms, traveling at 8 meters per second. So the van itself, the initial velocity of object 2, the van itself is traveling at 8.0 meters per second. As a result of the collision, the vehicles lock together and immediately come to rest. So if these both vehicles lock together and they both come to rest, but then the final velocity of object 1 and the final velocity of object 2, right? Question mark. Or rather, it's not question, it's 0, right? It's come to rest. So the final velocity of both objects come to rest. Or at rest. And so the question then says, well, calculate the speed of a collision, speed of a car before the collision. Right? They say before the collision while they're looking for the initial velocity of object 1. And so you have P before, right? So your total momentum before a collision is equal to your total momentum after a collision. I'm gonna run out of space again, aren't I? Probably. So P initial. Obviously, when you get to it, you probably don't need to write. As long as you know what you're doing, you can skip these 2 steps here. But I'm writing this out just so that you guys know like where everything comes from, right? So you don't get confused. Or if you're already confused, well, that's just unfortunate, right? You're gonna break this formula down. So mass, I'm definitely running out of space here. Actually, no. Let's go back in time. So both of these objects stick together, right? Both of these objects stick together and they come to rest, which means that we can treat these 2 objects as one entire object, right? Both these masses, they lock together, they come together, right? So we can treat this entire system as its own thing, right? Which is why I don't expand that. I'm going to expand this bottom row right here. And so because we're treating them as one entire thing, we're gonna have our mass total and final velocity. And so mass 1 is 1.1 times 10 to the third velocity 1, and that's the initial velocity of object 1, right? So plus mass 2, which is 2.5 times 10 to the third kg. And the initial velocity of object 2 is 8. Now, because the final velocity of both objects are 0, well, this entire side right here is 0 as well, right? So we can just ignore that. So this is, we bring this down 1.1 times 10 to the third plus 8 times 2.5 is going to give you 2 times 10 to the 4, right? Is equal to 0. So you minus 2 times 10 to the 4, right? Subtract that, subtract 2 times 10 to the 4 from both sides. And you have this, 1 is equal to negative 2 times 10 to the 4. And then you divide this on both sides. Divide this on both sides. And you get negative 1.8 times 10 to the 1, or negative 18 meters per second. I think negative 18.2, negative 18.2. So you'd get this. So 1.82, negative 18.2, like 0.2 is there. Okay. And again, we're treating these objects as one, which is why we can just treat the right hand side as like that. So a 3.1 kilogram gun is initially at rest, right? So you have 3.1. The mass of object 1 is 3.1 kg. It's initially at rest, so we can say that, well, the initial velocity of object 1 is at rest. And when a 0.0, so that's the mass of the second object, right? 0.015 kilograms, leaves the gun with a speed of 500 meters per second, right? So it leaves the gun. This is after, right? This is after this occurrence has occurred. I mean, well, I literally just explained it using its own word, but this is after the collision, right? Because there's a gunpowder explosion inside a gun, which fires the bullet. So this is after that occurrence. So we can say that, well, the final velocity of object 2, right? The final velocity of object 2, we'll put it up here. The final velocity of object 2, can I use a different color? Color that does not blend in. That's good. So the final velocity of object 2 is 500 meters per second. And then the question says, well, what is the speed of the gun? So they're asking, well, this was after this explosion inside the gun. Well, what is the final velocity of object 1? And now this color is broken. What is a color that can work everywhere? I guess that can work. So the final velocity of object 1 is question mark. What was the initial velocity of object 1? I mean, object 2, which is the bullet, right? What is the initial velocity of object 2? What is the initial velocity of this bullet before you fired the gun? Well, the bullet was in there. The bullet wasn't fired, and here you could assume that, well, my bullet hasn't been fired. It's pretty much doesn't go anywhere. So we can say that, well, the initial velocity of my bullet is 0. Right? The initial velocity of object 2 is 0. So we're just going to solve it, right? So we're going to do the momentum formula. Your momentum before a collision is equal to your momentum after a collision. And so your initial momentum of object 1 plus your initial momentum of object 2 is equal to your final momentum of object 1 plus your final momentum of object 2. I'm shopping around for good colors to use, right? I think orange. So the initial momentums of object 1 and 2, since your initial velocities are 0, you have no momentum. You don't have any momentum if you're at rest. So 0 plus 0 is equal to the final momentum of object 1. So mass 1, final momentum of object 1. Final velocity of object 1 plus mass 2, final velocity of object 2. And then what we can do here is we can just subtract this, right? Subtract this on both sides. And so now we have this. So is equal to mass 1 VF 1. And so now let's just substitute. So negative mass 2, your mass is 0.015. Final velocity of object 2 is 500. Is equal to mass 1, which is 3.1. And final velocity of object 1, which is what we're solving for. All right, 500 times this is 7.5, negative 7.5. I think. Yep. And then we divide 3.1 here. Divide 3.1. And we get 2.4. Negative 2.4 meters per second. Which makes sense because it should go in the other direction, right? The bullet is fired, it goes one direction, and well, then your bullet, and then your gun has a recoil, and your gun travels in the other direction, right? It all makes sense. Let's do 5D. So 4 kg cart, mass 1, 4.0 kg, moving at 3 meters per second to right. So the initial velocity of object 1 is 3.0 meters per second. Collides with a 6 kilogram cart, right? So the mass of object 2 is 6.0 kg, and it's moving to the left. So the initial velocity of object 2 is negative 3.0 because you're moving to the left. When the two carts collide, they lock together. So the magnitude of the total momentum of the two cart system after the collision is what? So they're looking for your total momentum after the collision. Well, this makes the problem a little bit easier because now we don't have to separate the right hand side, right? So we're doing the momentum before a collision is equal to the momentum after a collision. I'm gonna simplify this. I'm gonna just go straight to it, right? So mass 1, initial velocity of object 1 plus mass 2, initial velocity of object 2 is equal to your momentum afterwards, right? And so your mass here, your mass of object 1 is 4. Initial velocity of object 1 is 3 plus mass 2, which is 6, negative 3, momentum after. So 12 minus 18 is your momentum after. And then you have negative 6 kg is that. And that is the answer. Negative 6 kg times meters per second. All right, I'm not going to go into 5E and 5F because 5E is like 5C and 5F is like 5A, right? So I don't really need to do these two because they're pretty much the same type of questions. And for the sake of time of this video,